set? We're all set. So, all right, let's review what we did last time, which is a Carnot cycle. And between my own wackiness, I mean, Fridays are two hours lecture straight. I never do well on Fridays. I'm just kind of overwhelmed with so much stuff. My own class kind of jumble around a bit. So that's why I had a handout with the Carnot cycle. All of this, all the equations and the calculation of efficiency, which you recall ended up being, okay, the absolute value of the, I should be using a big delta for integrated work, but I just screwed up, so whatever. Divided by the heat added. Okay, so, or what do I want to say about this? Okay. Here, I'm probably jumping a little too fast. Remember that the whole cleverness to this was in a P versus B reciprocating engine. What Carnot figured out was that the starting point, you expand the cylinder, but it has to go back exactly to the place, which is the same idea as the crankshaft, right? The thing I didn't do such a great job drawing last time. An efficient engine is not a wind-up engine; it's a reciprocating engine. But he knew, he was clever enough to figure out before he keeled over a propeller rod, you can't just go directly back because basically the engine stalls. And the trick was to drop temperature, and before I drew it in a way that's actually the diesel cycle, which is just a straight drop in temperature. But instead what Carnot does is uses an adiabatic transition to cool, and then of course later heat in an adiabatic compression. So cool and adiabatic expansion. Now the reason that he did that was expansions are negative work. It helped, all right? And then, of course, you have to recompress to go back, to get that temperature back and get to your starting point. Anyway, so then I drew this big clunky thing right here. Remember that what this does for you is, you lose, geez, I'm not sure how to draw this. You lose, let me draw the diesel cycle, which is not on the, I don't think I have that on the test, which is just a straight drop in temperature. I like that. It's a little bit easier to express how the expansion is net negative and greater in magnitude than the compression, which is net positive, right? That's the storage of energy. And that's why you get a net negative work. The heat was always kind of funky to me. It's this step, the first step. That is heat added. And that's where gasoline was burned, and that's the only thing you as a person should ever care about. And let's see, what else can I tell you about this? Actually, I'm going to review a little bit more about heat, making sure you know the difference between positive and negative. But anyway, I'll go over that. I won't do it now. Regardless, heat was added in the first step. Technically, the second step, I suppose, heat is, well, sorry, this isn't isothermal, right? But it's hot. And yeah, anyway, heat's only transacted. Yeah, heat is transacted in the isothermal. Heat has to go in to keep the expansion. Heat has to come out in the compression to keep it cool. Heat comes in to keep it hot, and expansion heat comes out in compression to keep it cool. But okay, that totally makes sense. Okay, and so this ends up being 1 minus T cold over T hot. And what's remarkable about that is, and I'm going to expound upon a little bit more, is that you really cannot get a reciprocating engine to do better than this. And now, it does say that actually you can get 100% efficiency if your T cold is 0 or your T hot is infinite. So we're going to discount infinitely hot T hot. Infinitely hot engine block does not work. Well, not infinitely cold, 0 degrees cold, tailpipe, possible, but impractical to the point that it's mind-boggling. And when we do quantum mechanics, we're going to show that you can actually never hit 0 degrees K. You've maybe heard that in popular science. What's important is that, so practically this is never 1, it's always less than 1, right, between 0 and 1. And this again is you will never build a better engine than this, and you will never build a better reciprocating engine than this. And practically, you can never have pure efficiency, practically. And that means is that you can't turn all heat to work. Remember, we began all this Carnot jazz talking about one of the ways to state the second model is you can't turn all heat to work. if you can't turn all heat, heat added, which is what you pay for here, and you can't turn that into all net negative work and just minus plus, nature doesn't understand that, that's why I have an absolute value sign. You can't turn all that into work, your efficiency will never be 1.0, all right? So we just proved that. That's actually the big picture point, which probably got lost because there's just so much stuff here. So I think that's actually all I wanted to say about efficiency. We're still on the Carnot cycle, and now remember I mentioned that the Carnot engine is the best engine possible, and that's because of the entropy. The total entropy of the engine is actually, I'll just go ahead and tell you, it's going to be 0, but unfortunately I'm going to have to sit here and prove it, and that means, unfortunately, I remember all the algebra and tediousness of this. I got to do it again. Regardless, it's kind of important that you see this. It's just how, well, it's just what we do for whatever. Right or wrong, this is how we do it. And remember that that is reversible heat over temperature. I just told you that before, so let's just think back a little bit. A few lectures ago, changing heat is path dependent. That's an inexact differential. I even told you a little bit about the different paths you can take with heat, which is efficient heating versus inefficient heating. Don't remember that. I won't ever bring it up again. Regardless, when you took heat over temperature, all of a sudden the Euler criteria worked, and this is the whole thing. Q over T, not Q. Q over T is path independent, and therefore is a state function, and by the way, is entropy. I remember that actually last time I almost wrote, this is important for your unit section, I almost wrote S is equal to the partial of heat over T, and I knew that was wrong because I can't have a partial on one side and not have a partial on another. And in the next lecture, I'm going to tell you what entropy is. Remember, exact differentials, I'm going to define it as a differential, but remember that it has the form of not a change in S, but S equal. This is the change of S is equal. Next lecture, I will show you S is equal. It's actually much more complicated than this, unfortunately. Much more complicated than just integrating this. Remember, if I integrate this, I get, delta, big delta change in S, not partial little delta change in S. Okay, now to do this, what I'm going to do is add up all the heats. And the thing is, now I'm not going to write reversible because every step was reversible because I just made it that way. But just by definition, remember all the analysis was done reversibly. So I'm just going to add up the heat. Now just like, remember this, I added up the works, I added them. Now some of them were negative, right? A expansion, these were negative works and these were positive works. I just added them together. The fact that the first two were negative, meaning that they were actually subtracted, is their business. I simply added them. Subtraction is just the addition of a minus sign. Okay, something with a minus sign. So anyway, there's only two heat transactions. Remember, adiabatic transitions have no heat transactions. So that was technically the first and third. But tell you what, let's keep it. I don't need to change my terminology, but let's do this. Let's call it the hot step and the cold step. And never forget, the hot step is the one that we added gasoline. Okay, and therefore, and those were reversible, therefore the change in entropy. You see, I can't quite use this because the temperature changed, so I have to, I have to remind you that is the hot step over the hot temperature that part occurred at. Remember that there's a heat transaction to keep the temperature hot, and during the compression, you have to have a heat transaction to keep the temperature cold. Otherwise, that would not be isothermal. And so there you go. And let me tell you what, I'm just going to keep doing my derivation downward. This awkward room, this awkward board. Let me do the hot. Remind you the change in heat, that's hot. That was the change minus the change in work in the first step. Isothermal means that heat is minus work. Remember that I don't really have any formulas for heat. It always borrows work's formula isothermally. And so this was NR T hot. Notice the minus sign of work is gone because I defined that. Natural log. Okay, final, which is V2 over initial, which was V1. Okay, then we'll do the cold. And that's, of course, minus the third work step, which is NR. Of course, the gas was retained. I didn't actually open up any tailpipe. And I have to remember that the final volume was V1, V4 over V3. That's what can, remember that one tailpipe. When I started introducing this, I really stalled because I got confused. Right. The final volume is V4, the initial is V3. Remember, I got confused on that really badly last time. Okay. Now, I have to remind you something. I'm not going to go through all this. I hope you recall this because I don't want to spend 2 or 3 minutes rewriting this. But we derived that V3 over V4 was equal to V2 over V1. Now remember, that was because of the adiabatic legs connect. We were able to connect V2 to V3 by the second leg and V1 and V4 by the fourth leg through the adiabatic equations of state. Remember, that's Vf over Vi is equal to Ti over Tf to the Cv over Nr. Also, if any of you noticed the video, when I was actually writing that equation off cuff, I actually got that flipped, so I used the video editor to fix that. Anyway, that's why that video took me a day, because Microsoft Movie Maker makes everything very, very difficult. So, okay, anyway, so therefore, the change in the cold. Now you can imagine what I'm really trying to do here is, why am I using that? Because I want to put those heats with the same volumes, and so I'm going to do that with the cold one. And so the first thing I'm going to do is flip V3 and V4 so that it's like this, and so to do that I use a minus sign. And remember, if you need that in a derivation question, I will remind you, I will have the identity in the cheat sheet, which I will send Wednesday, that ln b over a is minus ln a over b. So there's that. Okay, now I can include this identity, minus nr t cold, ln v2 over v1. And you notice that now it basically looks the same thing. This cold heat looks like the hot heat. Right? They look pretty much similar. So actually the way to prove that is to take one and divide it by the other. I'll take the hot and I'll divide it by the cold. And okay, hot is nRT cold. No, what am I doing? I'm looking at the wrong one. Sorry, T hot. Right. And V2 over V1, you can see why I did this, because I eliminate everything but T hot and T cold, nRT cold, ln V2 over V1. I'm forgetting the minus sign. And so this is equal to minus T hot over T cold. T hot over T cold. Okay, sorry for all the, it's a bunch of detailed algebra. Help you a little bit there. I want to hit stop right now and just look at this sucker. And there's one thing, as much as this is a bunch of algebra, I want to think about what this means. Because right now I don't want you just looking at this and saying there was just a bunch of, fitting one equation into the other, cancellation of this and that, just algebraic simplification. Okay, I'm looking at the ratio of these two heats and I see a minus sign. Okay, again, this is, I don't think I'm going to put this on the test, but I might put it on the final, because at this point there's meaning in this. There's a minus sign to the two heats. What do you think that means? Now let me remind you that there was an analogy I told you. This isn't quite the answer, but it gets you thinking correctly. It's positive to store energy, right? The energy bank is positive to store energy. Right, now why am I saying positive? Because that's the what? Well, it's just the sign convention. Remember, that the energy bank is to remind you of the sign convention. It's positive to store heat. And if I'm trying to remind you what's positive, that means that there's a Okay, so now remember this is a ratio. There's no units, but there is a minus sign. Now what does that say about the relative directions of the two processes?
Overall release cold.
Well, now hold on. Remember, positive or negative is what? Why is anything positive or negative when it comes to heat transaction? Right, in or out. Okay, the ratio is negative, therefore their directionality is what? No, it's a ratio. That doesn't make sense. Only one of them is out, one is, the answer is one of them outs, one of them's in. Right? Somewhere there's a minus sign. If one of these is in, the other has to be out. Or vice versa, otherwise you don't pick up a minus sign, right? If they were both positive, the ratio is positive. If they were both negative, the ratio is still positive. Somewhere something got flipped, right? Remember the movie Labyrinth? Okay, you're not that old, but maybe you've seen it. Jennifer Connelly comes to one guard, one says the truth, one says a lie, which is the right road to take. You say, well, what would be the door that the other one would tell me? And then you take the opposite, right? Because the presence of the lie means that, okay, whatever. All right, so that means that they go in different directions. And that is very much a test question, by the way. I'm actually kicking myself for telling you that now because I would have loved to have put it on the test. And I didn't because I just said that. Okay, now when I'm looking at this and I'm reminding myself, I said this a minute ago, the first step is isothermal. It's an expansion. The gas ought to get cold. And that means that heat goes into the system to prevent that from happening. Is that positive or negative?
Positive.
Right, that's heat storage, right? Remember, it's positive to store energy. It makes sense. You know that an expanding gas should get cold, and it didn't. That's because heat came in from the outside and then vice versa. Heat had to come in. A compressing gas gets hot. It didn't get hot because by definition it was isothermal. Therefore, there is heat out, which would be negative. And what else want I say? And also remind the homework question, because I basically spilled my guts on that. Why were hydrogen and helium different in the Joule-Thomson? Why did they expand and get hot? Well, is the Joule-Thomson cylinder a Carnot cylinder? No, right. The magic cylinder, it follows adiabatic equations of state. Yes, if they compress, they will get hot, hydrogen and helium included. If the gas expands, they will get cold, hydrogen and helium included, but not in the Joule-Thomson dealing. And remember, if something's isothermal, that's because if I compressed it and it got hot, the heat escaped because it wasn't wrapped in glass wool. Anyway, so I'm sorry, I'm kind of reviewing and going over new stuff at the same time. I hope that's not getting lost there. Okay, last step in this, by the way, is, sorry about, again, I realized I painted myself into a corner. I want to point out that the hot transaction is minus the cold transaction modified by the ratio of the hot temperature and the cold temperature. Remember, temperature in the engine block divided by the temperature in the tailpipe, and therefore, sorry, this is awful. I'll just power through this and then I'll put this, I'll toss this up, you'll be able to see it in a second. So what I'm doing is I'm calculating the total entropy, which again I'm just writing as the hot transaction over the hot temperature added to the cold transaction over the cold temperature. And now I've got this relationship for the hot guy, which I now can see that's the change in the heat transaction in the third or cold step. T hot over T cold over T hot is 1 over T cold. Sorry, I'm just doing some algebra in my head. Plus the heat transaction in the cold step, third step. Maybe I got that wrong a second ago. And that's 0. Okay, sorry if you're having trouble seeing it. I'm standing in the rain. I actually do try to think about how I'm going to use the board before class, so I don't do what I just did right now, by the way. So there you go, net 0. And the point of this is, again, that as I'm going to expound upon a little further, for anything to behave with no entropy change means that it could not possibly have worked better, because entropy itself is the thing that states you can't turn all heat into work. And there was no entropy change inside of this sucker. Therefore, that rule is going to be followed to the best extent possible, meaning that this is going to be as efficient as it ever humanly can be, which unfortunately still states you can't turn all heat to work. So again, the ultimate proof is there. So big picture again, the Carnot cycle is a reciprocating engine with no change in its inside entropy, and yet the efficiency is still not 100%. So that's basically your proof right there. One thing here, let me give you a little hint on the homework. It speaks about this a little bit because probably, actually I didn't quite realize this until I taught this class a couple of times, but remember that, especially test 1 coming up Friday, that I've been using this terminology for work, reversible, irreversible, and I said your first introduction to reversible work was actually, expansion is the easy way to think about this. I'm pressing on the magic cylinder, and it's under 2 atmospheres, and I slowly let go. And then the other way, the second path was I'm pushing it 2 atmospheres, and I suddenly let go and of course jump out of the way, and the magic cylinder expands. That was irreversible. Notice I called a slow process reversible and a fast process irreversible versus slow and fast. That seems kind of awkward. Why would I use those words? Well, hopefully if you've done your homework, you may have noticed that when you do a reversible, I asked you to compress, well, virtual compression, right? You had a magic cylinder, and you compressed it, and you figured out the new state reversibly, and yada, 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 and it was hot, and whatever, and then you may notice that I began the next question with a reversible expansion, and the initial state of that expansion, it was a big hint, was the final state of the previous question. And what happens is that if I didn't actually ask you to calculate the final volume, I hinted at it in question 10. The final volume, actually the final everything is the initial everything. I'm talking, I think, what is this, question 5 to 6, I believe. So the initial state written at the beginning of this question, you will find is the exact same final state in the next question. Again, the first one's a compression, this next one's an expansion. And all the H's and U's that are, what would that be, plus here, they're minus there, right? Everything got canceled. The initial state and the final state are identical. That would be reversible, right? That's like the Carnot engine. Remember that I know it's kind of hard to see with a piston versus the crankshaft, but if I could do this analogy with the crankshaft, I started here and I did a full circle. I started here and did a full circle. It's just not as obvious with the piston. That's why I use the crankshaft analogy. Okay, now if it was irreversible, in which case I was pressurizing by a constant external pressure instead of slowly increasing the pressure, what you found was, okay, here's the initial state, and then you did an irreversible compression, and I believe, I gotta remind myself, I believe you can't quite compress as far, by the way, so I'll try to signify that by not perturbing. I actually am trying to do this in some kind of logical way, by the way, because it doesn't appear that way. So I don't think that it compresses as much. Don't hold me to that. I don't quite have the numbers in my head. Why would I? And when you let go, again, suddenly or irreversibly, and again, don't hold me to this, all right? I'm pretty sure about this, but I can't be totally sure about everything. Maybe I was in the matrix. Your expanded state actually will not return to the same temperature. It'll actually be hotter. And I think the expanded state would actually be a little bit larger volume. I think. Again, if I'm wrong, whatever. The point is that the initial state in question 7 and the final state in question 8, I think, those are not the same state. Right, so you see my point about reversible? Again, everything is pushed slowly, let go slowly, and you end at exactly your starting point. But irreversible, that will not be the case. And the reason that I'm pretty sure that I'm right, that the ending state has a larger volume and actually did not return to 100 degrees Celsius, it actually returned at the the final state in the second question was hotter is because that would have more entropy. More volume, more heat is more entropy, which hopefully you kind of have a gut feeling that's correct. If not, I'm going to do the equations right now to show you that's the case. So, anyway, so you kind of see why the reversible, well, hopefully you see what reversible actually means. That was the point of the homework question. I know it's a really long question, the hardest question I could have asked, but the point is to actually redefine reversibly and irreversibly. I had to use the word reversible and irreversible because those are the correct words, but what's frustrating for me is I couldn't tell you why I was calling it that because we hadn't covered entropy yet. Okay, so, all right, so the equations for entropy, heat over temperature, but that's not really that useful. I can give you better equations for entropy, which of course I'm going to hijack work. And I've got 4 conditions. I'm going to have to do isothermal reversible, isothermal irreversible. And I have to do adiabatic reversible and adiabatic irreversible. And I'm probably going to put this on the test. Now I didn't have it on the homework, and it says Monday, which is kind of cutting it close. However, I feel like this is a giveaway. Let me do it, and then you'll hopefully agree. I'm giving points away. Okay, so change of S is what? Okay. So forget Carnot, this or that. You're on the test, and you've got 2 questions. I'm saying that because I know you have 2 questions where a gas expands, a gas contracts, and one of them I'm going to ask you to calculate the change in entropy. Why? Because these calculations are impossibly easy. That's why. So forget the Carnot stuff. And of course, it's going to say half a mole expands, the temperature is this. Okay, let's do isothermal and let's do irreversible. And of course, what I've got is, let's do the change in U, which is 0, and forget your units, which is, of course, a change in heat, plus the change in work, and I guess I would need to integrate those. Now, because this is 0, the change in heat is minus the change in work, which is nRT ln, is what I just did, dF over VI. Okay, and therefore, the change in entropy is the change in heat over, you know what? I technically, sorry, I need to, trying to be exact about this, I need to integrate those. So I need to integrate this too. Do not worry about this. If you put partial versus integrated partial, which is delta, I will not count off because I'm screwing that up. I just try to do this very carefully. Just 1 second. Okay, so the change. Remember, I'm hijacking work's equation for heat, nRT over T ln dF over VI. Okay, and that's nR ln dF over VI. Okay, could not be more simple. Question.
Isn't that the formula for reversible work?
Oh yeah, right, because you know what? It doesn't matter. It doesn't matter. Remember that entropy is an exact differential. It's path dependent. Path independent. I hate that. Path independent. Reversible and irreversible are our paths. I know it can be a little confusing. Constant volume, constant pressure. There's a little bit of that jazz in there too. But for the most part, reversible, irreversible are paths. They change the work, and they would change the heat. But entropy is defined. Here, let me. You don't need to write this down. Entropy is defined as the change in reversible heat over temperature. I was ignoring that up there. No, I didn't. I did get it right. Sometimes I screw up and I tend to forget that heat, in entropy's case, is reversible. That's actually, remember I was saying this last time, I find this kind of cheap, but entropy is path independent, but heat is path dependent. So the conundrum is resolved by stipulating that entropy is always a reversible heat. And once you've chosen a path, you're technically path independent. And I can't believe I'm saying that. That sounds like BS to me, but it is true, and you can measure it. It is perfect. So notice that I actually was setting you up. You beat me to it. I was setting you up talking about irreversible transitions, but it didn't matter. It's applicable to both reversible and irreversible. I swear I was going to say that next. You believe that. Okay, so look, folks. Test. The life of the universe and everything section, a gas expands, a gas contracts. I'm going to put entropy on there because all you have to do is, like, this stuff is given, maybe it's given in a snarky way. Well, of course, N I have to give you, R is 8.314. Right, this is, I'm sorry I'm only covering it now, but this is a giveaway. This is shockingly easy. And it doesn't matter whether I say that the gas expands reversibly or irreversibly, it's the same formula. Right? So this could not be easier. Now let me give you an example of a derivation question. I'm not going to ask this, by the way, because I'm just going to stick entropy calculations. I'm going to just stick to this. Second exam. The reason I'm even bringing this up now is because second exam, absolutely. Let me give you an example of how else I could do this derivation. Sorry, you know what? Yeah, here's where I screwed up. I should have had the reversible right there, by definition. But my bad. Okay, so if it is still true that heat is minus work, and again, I can put a little reversible there, what I could do is integrate to get the total change in entropy. I could integrate P dV, because that's minus reversible work, right? Now folks, I'm not going to, in case you're worried, I'm not going to have on the test show me 2 ways to derive a change in entropy. That's a task of memorization which only the people who haven't programmed their calculator can answer. I'm not going to do that. The point here is to see that there are often multiple ways. This is actually good news. There are multiple ways to do derivation. In fact, there are probably thousands. In fact, almost every class, on all the derivation questions I ask in homework tests and yada, 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 someone inevitably comes up with a brand new one every year. It's kind of slowed down over time because I've seen a lot at this point. Regardless, so P over T delta V, right?
N over 2 would be...
Well, hold on. Big picture. I'm integrating volume. If I'm going to integrate volume, I better see all the other... All the V's need to be transparent. There can't be any V's on this side. And if I have a dV, there better not be any other V's there. If I'm just going to turn a partial V into delta V. If there's another V in here, I need to know it. Is there?
Set the pressure.
Pressure is nRT over V. So that's nR over V. Right? You see what I mean? You can't hide variables like that and then integrate them, because that would be changing the volume at constant volume. Again, if I had just, as I was trying to trick you, if I took that P over T outside and integrated the partial V to delta V, that would have been to say that volume was constant, and I'm integrating volume. That's scientific nonsense, mathematical nonsense even. And of course, the definite integral of 1 over x is nr ln upper limit over lower limit df over di. Okay, again, there are multiple ways to do this. The news, not to overwhelm you, is actually in your favor. When I ask you to do a derivation, and you don't remember the way that you're trying to remember to do it, there's another way to do it, right? And you might just think of that one. You may think of something I've never seen it before. If it's right, I count it correct. And I do this every year. Okay, so isothermal, reversible, and irreversible. Question?
What is the T?
Wait, I'm sorry?
Oh, the T counts as well? Oh, yeah.
Oh, yeah. Q, nRT over VT.
Okay.
Yeah. So they match, right? And also notice that here's another thing. Look, the units work. Let's see, joules per K mole, so that's joules per K. And entropy ought to be joules per K. Let's see here, joules per K. Natural logs don't have units. That doesn't make sense. Besides, the units are canceled. And I end up with joules per K. So I know it's right. I'm certain it's right. If I doubted it, Okay, on the cheat sheet, and you see all the formulas, and you think something's not right, do the units, right? I told you that's how I've gotten out of some issues in like graduate level research. Okay, real quick, now we have to do adiabatic, and this one's pretty easy. So, and you can imagine, all right, so notice that I'm not trying to trick you. I'm not saying reversible or irreversible. And I'm not likely to put an adiabatic transition on the first test because, well, don't hold me to that, but the adiabatic or irreversible, those, as you're doing your homework, that really is a pain, isn't it? So I don't want to test your ability to use a calculator. Okay, now the way to do this one is I'm looking for the change in entropy. Again, I'm going to be careful about my math. It's okay if you're not. On the test, you know, whether you remember to put a little integral sign and change your little d's to big d's. Okay, now the way to do this is to remember that, let's see. Yeah, this is where this is a real pain. This is why I always struggle. This is why I do adiabatic last. Is that remember that there's technically no heat transaction, yet what I'm going to do is use the concept of internal heat. Just because I wrapped the magic cylinder in glass wool didn't mean that the temperature suddenly shot to 0 K. That doesn't make any sense, right? And so what you do is you know that there's a temperature change and the change, well, what am I doing? Basically doing a change in U, and so the relevant energy is CV dT. Okay, so there you go. That's how you can figure out, again, this is why adiabatic is kind of a pain, is because when you say that there's no heat transaction, you automatically just say, well, there's no heat at all, and that's not true. And the way you take into account heat, which is temperature, the way you take into account the changes in that quantity is by heat capacity, right? So integrate it, and then this ends up being CV ln TF over TI. Okay, now let me remind you that heat capacity that I will give you on the test, I'm going to give you per mole. Stop there to be consistent. Remember that I'm going to give you values I find on the internet. If you're having to do this, I'm sorry, this is too ugly. OCD is kicking in. I'm going to give you values for oxygen or nitrogen, whichever one I choose. I use the value I find on Google. It will be in units of joules per K per mole. That is not correct because heat capacities are joules per K, just like entropy. So you've got to remember to multiply that by the number of moles. Okay, sorry, let me, again, I'm going to be exact with my mathematical symbology here. Okay. This isn't quite right, because why did the temperature change to begin with? Right, for one, it was adiabatic, so the first thing I did is I took the magic cylinder, I wrapped it up in glass wool, and then I did what? Let's make it hot. How do I make it hot? Compress. Okay, so NR ln dF over DI. Okay. They both count, by the way. So remember that there was, the easy way to think about this is that you actually have to use the force a little bit, but you can imagine I compress the gas first, which results in a change in entropy. And that, of course, heated up the gas because it's wrapped in glass wool, and that also results in a change in entropy. Question?
Is that adding them together, or is that just
No, yeah, they're added together.
Okay.
Yeah. Okay, it's a little bit easier if I do it that way, isn't it? Now, here's a funny thing is that on the cheat sheet, I'm only going to give you this formula for entropy because it works no matter what. Remember, isothermal or adiabatic, reversible and irreversible are irrelevant because this is a state function. Notice how the change in U was 0 for isothermal, whether it was reversible or irreversible. The change in H was 0. Isothermal, regardless if you're reversible or irreversible, right? That's path independence. S, this is the right equation, really no matter what, because if you're adiabatic, then you figure out your T's and your V's, and then you have it. If you're isothermal, this term just goes away, right? ln of 1 is 0, right? So even if you do an isothermal question and you do it this way, I'm going to give you full credit as well, because you're going to get 0 if you did it right and get full credit. Right? So, but if you write that down and carry it through, even though you kind of should, it's fine because you're going to get 0. So there you go. Again, I'm going to have one question where I will have you calculate entropy, and I don't like doing that because it's not been on the homework, but really, folks, really, I think I'm going to do it because I feel like I'm just giving you points. Because, can you use a calculator? That's the actual question. Test 2, right, and I'm pretty sure you can. Remember your calculators. I've only got one extra, all right? It's just too easy. It's too easy. I can't not do it. Okay, last bit. Okay, done with test 1. Don't leave. Don't leave. Anyway, I need to go over something while this is running around in your head about total entropy. And it's really important I bring it up now. I kind of would like to cancel class, but cancel class, give you that extra 5 minutes I never have. But because we're here and you're thinking about this, let me restate the second law. Remember that the second law can be stated 2 ways. You can't turn all heat to work. And total entropy of a spontaneous, I hate that word, a spontaneous process increases. So entropy always rises. That's probably what you hear maybe in high school or something. You start hearing that this stuff even exists, right? Total entropy always rises. And the thing about this is there's a little bit of a trick here in that I said total entropy. Now, actually, I kind of screwed up earlier. Okay, I erased it. No, I didn't. Okay, this was kind of a mistake, by the way. I shouldn't have said total entropy here. This is the entropy of the system. Total entropy, sorry about that. Yeah, my bad. I can't even fix that on the video, by the way. I hate that. That's the total entropy of the interior that I used. I really should not have written it that way. Total entropy is going to be the entropy of the system plus, guess what else? Surroundings. System plus surroundings. Now, we have never, in case it's not clear, we have not dealt with the surroundings ever. Why would we? We only care about the magic cylinder. I mean, what goes on the outside includes the whole universe, and that's a little too much to worry about. In the case of total entropy, then you need to take into account the entropy change of the system and surroundings if the surrounding entropy changes. Surrounding entropy changes, we're going to make an approximation. Surrounding entropy changes due to a heat transaction. And it's easiest, in case you get confused on the test, second test or the final, if the magic cylinder is compressed and heat's released isothermally, then the entropy of the outside would increase, right? That makes sense. Again, if heat is shed in a process, the outside entropy increases. Now, don't try to memorize that. Your gut should tell you that that's the case, right? Just, if I ask that, just say to yourself, well, what should happen? And you're right? This is why PChem 1 is practical. Your instincts are actually correct in this class. In PChem 2, it won't be. The exact opposite will be true. But you'll get used to that. So anyway, in this case, you can use your instinct. The entropy is only, entropy of the outside is changed in a heat transaction, and that means adiabatic changes have no outside entropy change. Anyway, so what I need to know is that total entropy. So you see, this is why I screwed up. I shouldn't have called that S-toast. This is what you've been calculating the whole time, or more accurately since an hour ago. Entropy change of the system plus the entropy change of the surroundings. And of course, I'm going to abbreviate that by SURR. So remember, I said this when I talked about pressure. If I don't give a subscript, it's the system. And that's going to be about 99% of the time. Surroundings will be surroundings, SURR, and the total is total. Okay, again, this is important because the second law is not about the system, it's about system and surroundings. Right? And so I can't worry so much about this. See, this might negate that, and actually that often is the case. So I need to, anyway, so I need to do the total. So I'm kind of out of time, but let me just point out to you that, so just remember this, but let me just point out to you where we're going, which we're going to pick up on next Monday. If the change in system, and this is isothermal. Okay, so again, this is by definition, and I'm talking about isothermal. Adiabatic changes in surroundings will be 0 because there's no heat transaction. So I'm doing the change in the surroundings, and again, I'm doing isothermal. What do you think it is, if this is the heat into the system that came from the outside, what do you think, what's the heat transaction, not from the interior's perspective, which is this, because this is all we've been doing, what do you think the heat transaction is from the exterior's perspective? Negative. Right, it's minus Q. Okay. Now notice that if a process is technically, if the total entropy change is 0, these are perfectly matched, and that would be reversible. And if not, then actually the surrounding, well, they won't balance in such a way to totally generate entropy. Anyway, look, I'm saying too much because I'm done. Anyway.